Start recording here. So, oh, put them in the wrong place, but whatever. Okay, so you got a lot of stuff, right? Let's just kind of talk about each one. So like I said, this is just an old version of the formula sheet that I had printed already, so may as well save some paper. Like I said, if anything, you might just, oh, thank you. Oh, put your name on it. So if anything, you'll have more information than this. But because we're starting chapter 2 today, I wanted you to have an idea of the formulas that you'll have. Okay. And then I'll print off revised copies. But because I already had these hanging around in my office, I figured may as well use them. Okay. You'll notice if you flip through, there's some tables as well. Okay. These tables are the ones that we'll use. Awesome. Thank you. One, two, and great. Okay, so those tables, they're yours to kind of just use for homework or whatever. And then, of course, for the test, I'll print up, or I'll have fresh ones for you to use, but they'll be the same. Okay. So there's that. Then I gave you this one with the glaring typo, very first thing, visualizing, doesn't matter. In Swedish, there's a saying, fort och fel, quick and wrong. So that's what happened here. Quick and wrong, and so doesn't matter. What happened is I had it written in a markdown file, and as you know, so you'll see those 2 stars, which we looked at in the lab, right? And then I decided, you know what, I'm just going to work it over in LaTeX because it is easier to see page breaks and stuff. And some things got lost, and there's no spell check. So you'll see there's typos. But why I wanted to print it off for you is mostly, well, I guess there's graphs on the back, right? So you can have a look at the graphs when we get to them. Okay, so this kind of 2-leaf one is for section 1.7, okay, which we're gonna just quickly kind of rattle off today. And then a little bit more refined looking, I typed up the notes for chapter 2, just everything that you'll need for chapter 2. Again, just kind of a first pass at it. So of course we'll kind of fill in the blanks here. Okay. But as far as all the formulas and all the writing goes, or most of the writing goes, I typed it up instead. Okay. Any questions? Great. So this is kind of new to me. I never type up my notes, so congratulations. You saved yourself some writing. But it's going to be weird for me, I guess. Now what? Oh, so let's start going through section 1.7. So last day, right, we finished 1.6, which was a big section, right, where we talked about things like how do we find the mean? How do we find the median? How do we find outliers? How do we find, how do we make a box plot? How do we make a stem and leaf plot? Right, so we talked about all those things. I'm not going to make them in a list because I'm kind of moving on, right? We wrapped that up last day. But today we're going to start section 1.7, which is just visualizing and summarizing categorical data. Okay. So before, we've been talking about numerical data, right? Those have all been measurements where we can actually talk about the average, right? And so now we're changing gears and we're going to talk about what do we do with categorical data, right? So visualizing and summarizing categorical data. And I think that's the one question, I forgot to mention it in class last day, but it's the one question on the assignment that we haven't quite covered yet. Part one, question one, part D, right? Because the lab section variable is a categorical variable, okay. But well, I guess I'll just tell you now. So we have a couple of options for categorical data. So remember, categorical data is when you have a list of information, but all that information can be put into categories, right? Distinct categories. Okay. Things like hair color, your grade, right, as a letter grade, all kinds of things. Right? Even area of where you live, right? So a lot of things can either be reported as categories, or even we could take numerical variables and turn them into categories if we wanted to, right? And so we could say, okay, well, how old are you, right? That would be a numerical variable. But then if we put it into categories, right? 18 to 25 is a category, 26 to 30 is another category, right? So we can create categories out of numerical variables, and we do that sometimes. Okay. But as far as visualizing, we'll start with the visualizing. A numeric or a categorical variable goes. You've probably seen pie charts. I'm here to tell you or ask you to please don't use pie charts, and I'll explain, or I'll give you some reasons why. Okay. We should be using bar graphs or bar charts. So I'll use graphs, charts, and plots interchangeably. Okay. And so we should be using bar graphs for categorical data. And so that's going to look essentially like a histogram, except each bar is representing a category. Right. And so typically when we display them, we put a little space between the bars just to indicate that it's not a continuous distribution. Okay. And so I'll just take it's on your sheet, but just emphasize it here. So for categorical data, or for visualizing, I'll say, for visualizing categorical data, we should use bar graphs. Okay. I'll just make a note here that, like I said, because some people are thrown off by, sometimes I'll say a bar plot, sometimes I'll say a bar graph, I'll even say a bar chart, but a graph is a chart, which is a plot. I'll use those all interchangeably. Okay. So a bar graph is the same as a bar chart, which is the same as a bar plot. Same thing for pies. Okay. I only make a note of that because I know that can be confusing when you're just kind of learning all this stuff and you hear different terminology and you're trying to stay on top of it, but then I start using different terms and it gets difficult, right? And so I just want you to be on board with that. They're all the same. Okay. And so a bar graph, right, is like a histogram. So it's going to look something like this. And you have a way nicer example in the printout. right? Here we have category A, and here we have category B. So the heights of the bars just represent how many are in each category, right? And so a taller bar means you have more in that category, right? So pretty self-explanatory. Oh, I do want to make a note about these notes that I gave you. And so I do have the R code in there, right, for making a table, which we haven't seen yet. It's not something that I want you to kind of study or anything. Because I was gonna do it in the background anyways, I figured I may as well show it to you, because eventually we will be making tables. And so I'll just show you what it looks like. Okay. And so, yeah, a lot of this stuff. So I'm using, in the notes, I decided to go with a built-in data set, which is called MT Cars. There's a little footnote at the bottom. So it's the 1974 Motor Trend US magazine. They looked at the fuel consumption and then 10 other aspects of cars, okay, for 32 cars. Okay. And so I've listed all those variables, and just as practice, what you can do is you can go through and try to figure out, just by the description, which one's numerical and which one's categorical. Okay. We won't do that together, but might be good practice. And so let's see here. I guess it makes more sense to go in here. I put it in the wrong place. Looks a little bit nicer in color. Okay. So we should be using bar graphs. That's my take-home message. Okay. So what I want to do is, well, first, I just picked the first categorical variable in the list, and that's the number of cylinders, right? And so this one here is categorical. Miles per gallon, right? That's a measurement. And so this one's going to be numerical. So like I said, it'll be good practice if you just go through those. And even just by reading those descriptions, you'll most likely be able to tell which one's numerical and which one's categorical. Okay. So for this little example, I decided to use the number of cylinders, right? And so when we make a table of the number of cylinders, we can have either 4, 6, or 8 cylinders. Okay. So these are the categories. And these are the counts. Oh. Does anyone else not have a copy? Oh, I'll skip. Sorry. So what I want us to do is just have a look at, so I made a pie chart. I think we all know what a pie chart looks like, right? It's a circle, and each slice is supposed to represent the size of each category, right? And so here, what I want you to consider is just at a glance. So remember, the whole point of visualizing data, right, is to be able to just glance at something and say, oh, I see what's going on there, right? And so at a glance here, right, is it jumping out obvious which slice is the biggest? We have some time, right? We could probably get a little nitpicky and probably guess this one. But most likely what we would want to do, just to confirm it, is you would go back to the table and say, oh, okay, yeah, so 8 cylinders does have the highest count. So, okay, good, that was right. And that's not really the point of visualizing data, right? And so by comparison, right, if we look at the bar graph, even with just the raw counts, right, because these are just the raw counts, it's pretty obvious which bar is the highest, right? And so that's why we should be using bar graphs instead of pie charts. So a lot of people like pie charts just because they, I don't know, for some reason they look nicer to people. But as far as kind of how useful they are, in comparison, I think this one's way more useful. One argument you could make, if you were trying to make a pie chart, is, well, you could just add labels for the size of each thing, right? But again, that would work against the principle of, okay, clear and concise graphics, right? Because now you're crowding it with information that, so this information would just be a table, right? And so you could just give the table, right, and not visualize it. Another thing, pie charts are really only glaringly obvious if you only have two categories, right? So 70% males, 30% females, right? But something like that, you could just represent with one number, right? If I tell you, oh, there were 70% males, do you know how many females there were? Right? 30%, right? And so you want to kind of steer clear of pie charts, just word to the wise, okay? Because often a pie chart can just as easily and more effectively be communicated in a table. Okay? So all those little notes are on here, but I just blah, blah, blah. Okay? Any questions about that? And now you know how to argue against the pie chart too. Oh, you used the pie chart? What were you thinking? You could have communicated that in a table, but no. So often we want to look at more than one categorical variable, right? And so if we go to the next categorical variable in the list here, we've got this yes variable, which is just if you have a V-shaped engine or a straight engine. I don't know what that means, but I'm assuming something looks like a V and something doesn't. Doesn't matter. But so here, right, one thing to note is 0, right, is denoting the V-shaped category. And so we do that quite a bit, where we use a number to denote a category. Right? So even if you're seeing numbers, they might still be categories. And so here, we're using numbers to denote categories. Right? So even if you're glancing at a data set and all you see is numbers, that doesn't necessarily mean that you don't have any categorical variables, right? You'd have to read the description and say, oh, actually this VS variable, right? 0 means it's V-shaped, 1 means it's straight, and there won't be any other values in there. So when we look at the table for it, right, so we've already seen this, the table for the cylinders, 4, 6, and 8. Now here, if we look at the table for the VS, 0 was that it was V-shaped and 1 was straight. And again, here we have the counts. So we could look at each of these categories individually, but I think we're all on board with, if we want to get some sort of information, deeper information, right, we would have to look at how do these categories compare to each other, right? And so what we do is we make a contingency table. Okay? So here, this is a contingency table. I'll clean up contingency. So you can imagine that there's kind of lines going like this. So here we've got our VS variable, and here we've got our cylinder variable. So now we're able to look at, okay, well, how many V-shaped engines were four-cylinder engines? 1 out of the 32. And so now we're able to break it up and look at, okay, well, how does one variable compare to the other? And so, pretty interesting, right? It looks like the four cylinders are just often straight engines. I don't know what that means, but like I said, it doesn't matter. And also the 8 cylinders, they're all V-shaped. And so 6 cylinders, roughly the same, right, for each V-shaped or straight. So I don't know what that tells us, but that's a fact, right? And so we've got this shifted distribution, right? Where if you have a 4-cylinder, it looks like it's more likely that you're going to have a straight engine. Whereas if you have 8 cylinders, it looks like it's more likely that you'll have a V-shaped engine. And if you have 6 cylinders, who knows? 50-50 split. Okay. So here, we've been dealing with the raw counts, right? 10 engines or 10 cars have the 4-cylinder straight engine. Right? And so what we should be doing is we should be talking about proportions or percentages. So in general, I don't know if I should put it on here or I've already got it on here. I'll just highlight it, I guess. When reporting on categorical data, we should use proportions. Highlighter's huge. So later on, right, we'll most likely just be talking about proportions. And a proportion is just the number in a category over n. N, remember, is the total sample size. N is the sample size. So what we're doing here, right, we had 32 cars in our data set. Right, so our sample size would be 32. And so if we wanted to make a table of proportions, we would take 1 over 32, 10 over 32, right, and convert these all to proportions. What percentage out of the 32 cars satisfy each of those criteria? And so that's what we have here. Here we have a proportions table. So here we've got a table of proportions. But it's the same idea, right? We've got the V-shaped and the cylinder. And I do just want to emphasize that even though I have this R code in here, I've only included the stuff that you'll see along the way. The lecture tests, right? So the tests and the final exam will have nothing to do with the R code, right? And so I'll expect you to be able to read something like a summary, right, from R. But as far as testing you on how do I make a table of this, no, that's not going to happen, right? And so I'm just giving it to you because you'll see it along the way, and now you've kind of seen it in context, right? But as far as testing you, how do you make a table of the proportions? No, we're not doing that. So I just want to highlight that because that could be overwhelming. Okay. So, table like this, especially if we have more than 2 or 3 categories, could get a little out of hand, right, just for looking at it. And so then especially we would want to visualize it somehow, right? And so what we do is we've got 2 options, and I've shown them to you here. If you go to the last page. I just use the raw counts. I got lazy. Should have used the proportions, but wouldn't really make a difference. So here, we've got 2 options. I like the second option. The second option is where each of the categories, right, are 0. So here you've got 4-cylinder, 6-cylinder, 8-cylinder within the V-shaped category. Right? And then here within the straight engine category, you've got 4-cylinder, 6-cylinder, and then no 8 cylinders. Right? So I like the look of these kind of side-by-side bar plots. We're still making bar plots, but because we have more than one set of categories, right, we have to kind of slice and dice them. Here is a segmented bar plot, which we could do too, right? So of this many zeros, right? So of this many V-shaped engines, this many are 4-cylinder, this many are 6-cylinder, and this many are 8-cylinder. And so we could look at it that way. I didn't bother moving the legend, but again, just kind of quick here. But I don't know, for some reason, I don't like this one. They're both equally valid. So whichever one you like more, go for it. But like I said, I like to put them all side by side, group them together. That's just. Any questions about that? No? So, another scenario, right, that we have to consider is what if we've got some sort of numerical data, right? So I'm just kind of here. Which is on the 3rd page at the bottom. It bumps my graphs to the next page if they're too big. So we've looked at, okay, how do we compare a numerical variable? What do we look for? We make a histogram, we look at the distribution, right? That's numerical variables. Now we've looked at categorical variables, looking at the relationship between 2 categorical variables even. But now what if we have a numerical variable that we want to look at? How does it behave across groups, right? And so here, right, we've got a numerical variable And if we're talking groups, right, we're talking a categorical variable. So we'll talk more about it later in the course, but for now, right, we just want to look at it, right? How do we look at something like this? And so we're going to make side-by-side box plots. There's lots of options. For example, if we wanted to look at the miles per gallon for each of the cars by the cylinders, right? So what's the fuel efficiency essentially depending on the number of cylinders that we have, right? So if you think about your data set, we've got the fuel efficiency for each of the cars, and then we can group them. Okay, so all the 4 cylinders go here, all the 6 cylinders go here, all the 8 cylinders go here. Right? And then we'd have little split up numerical data sets, right? The miles per gallon for each of those groups. So one thing we could do is we could make little subsets, right? Pull out all the 4 cylinders, make a histogram of the miles per gallon in that group, right? Pull out all the 6 cylinders, make a histogram of the miles per gallon in that group, and then try to compare them. But like I said, we'll use a side-by-side box plot, which is this last plot. And this is kind of the more important box plot. I'll never make you draw a side-by-side box plot. I'll only make you draw one. Right? But because we looked at it last day, right, we know the anatomy of a box plot. And so now, right, we see that, okay, here's the median, right, just looking at this one for a second, right, the 4-cylinder cars. Here in the middle, we've got the median fuel efficiency, right, the median miles per gallon for a 4-cylinder car. Here's the median for the median miles per gallon for a 6-cylinder car, median miles per gallon for an 8-cylinder car. There's a trend here, right? It looks like as the number of cylinders increases, the fuel efficiency is going down. The number of miles per gallon that we get seems to be decreasing. Okay. So we've got the median, we've got the first quartile, the third quartile, and then it looks like there are no outliers here. So outliers, we've only got one in the 8-cylinder group. And so we can look at these and say, oh, okay, well, I can see a difference here. If they all looked essentially the same, right, then each of the groups we would say are roughly similar. So if we're looking at these and saying, well, the median's about the same, so say this was moved up here, even though down here, right, we moved it up here, then we would say, okay, well, then across these groups, we've got the essentially the same thing going on. But here it's clear that we've got a difference between each of these groups. So, oops. There appears to be a difference in miles per gallon across the 4, 6, and 8-cylinder groups. Any questions about that? So that's where we'll leave categorical data for now. Just kind of visualizing, summarizing. We'll put that on the back burner for a little bit. we'll change gears to chapter 2. So let me just grab it here. Oops. And looks a little bit more refined, but there's still no spell checks, so we'll see how it goes. I just wanted to have something for you guys, because otherwise this is a lot of just kind of writing and definitions. So chapter 2 is kind of its own realm. So if chapter 2 doesn't feel that fun, don't worry, it's not. It's just kind of something that we have to get through, get done, and then we'll be able to do kind of more fun, but also more related things, right? So once we get into chapter 3, everything after that will be related to each other. Whereas I feel like the beginning of this course, chapter 1, we kind of introduce all these things, and then we go to chapter 2 and it's a bunch of new stuff, weird stuff, and then we get into just kind of doing the same thing over and over again. A lot of people, when you say you're doing stats or taking a stats course, they think this kind of probability. Okay? We'll be dealing with probability quite a bit, but this section deals with a very kind of separate group of probability, like counting cards, right? So combinatorics, all that kind of not so fun stuff. I don't enjoy it, but that's my problem, I guess. A lot of people really love it, so. But that's why I wanted to just print out the notes so that you have what you need, and then you can just kind of talk about it, do some examples. I'll show you it's not so bad, and then we'll get through it. So, like I said, we'll be dealing with probability, and we'll be talking about probability throughout the rest of the course, right? After all, we are talking stats here, so in one way or another, we are going to talk probability, but chapter 2 is the only one that I'll call probability. And so the probability of an outcome, the definition here, is the proportion of times that the outcome would occur if we observe the random process an infinite number of times. And so if I asked you, if I flip a coin right now, what's the probability of getting tails? 50-50, right? And so we know that, right? And so we don't need to flip a coin an infinite number of times, mostly because we can't, but also we don't need to do that because we know that the behavior of a coin wouldn't change. We know that there's two sides, right? And each side happens randomly. Right? And so that's the definition of a random process, is just a process which yields a set of outcomes just randomly. So a random process are things like you roll a die or you flip a coin, right? So all these things are random. And even though we get kind of hung up on, oh no, I've flipped too many tails already, the next one has to be heads. That's not how it works, right? And so the probability of flipping, I don't know, 5 tails in a row, it's not that high, but it can still happen, right? And so the probability of flipping another tail is still 50-50. So we kind of betray ourselves in thinking that this random process is actually dependent, right? It doesn't care. The coin doesn't care. and it'll always be a 50-50 probability. Same with rolling an unbiased die is what we like to say. But I mean, we can just assume that all dies are unbiased, right? So then we have a set of outcomes, 1, 2, 3, 4, 5, 6. And so these are random processes, right? Rolling a die, flipping a coin, and we have this set of outcomes. So the set of possible outcomes is the sample space, which I guess I have on here already. So a set of possible outcomes is the sample space, denoted by S. One thing that's not, glaringly obvious until you point it out is that the words probability, proportion, and even percentage, we can use interchangeably. And so all these, the 3 P's, they're all the same, right? I have roughly equal to percentage, right? Because a proportion times 100% is a percentage, right? So they're not exactly equal, but a probability is just a proportion, which is essentially a percentage. Right? So I could ask you to find the percentage of whatever, or the probability of this happening, or the proportion of outcomes, and they would all mean the same thing. So you'll see on your formula sheet, right, I've got it broken up into chapter 2. In here, we use probability notation, right? Probability notation is something like P of A is probability notation. So how we read it is just like in the lab, if we have some sort of function followed by brackets, right, we read the brackets as up. Right? And so if we have something like P of A, we just read it as the probability of A, where A is just denoting some sort of random process. Where A denotes a random process, oops, or outcome. So a lot of the time when we're working on a problem and we know the context of the problem, right, we could say something like P of H, right? And H would mean you flipped a coin and the probability of getting heads is 0.5. P of T, right, knowing the context, right, you flipped a coin, the probability of getting tails is 0.5. As long as you know the context, right, P of 2, assuming that this 2 means you rolled a die, right, and you rolled a 2 on the 6-sided die, then 2 is just one of 6 options. And so the probability of rolling a 2 is 1 in 6. So let's talk about some probability facts. Okay? So a probability has to be between 0 and 1. Right? Think about percentages. Right? A percentage is between 0 and 100. A proportion is between 0 and 1, and so a probability is between 0 and 1. So that's just a fact. If it's not between 0 and 1, it's not a probability, or it's not a proportion. So the second fact is that the total probability in your sample space has to total 1. Right? Because if you've looked at all possible outcomes and added up the probabilities, it has to be 100%, right? Or just 1. Because otherwise, if it's not 100 or 100% or 1, you haven't looked at all the possible outcomes. So if we look at the total probabilities for rolling a die, right, we've got 1 over 6 plus 1 over 6 plus 1 over 6. Right? Each of these occurs randomly, right, with a probability of 1 over 6 each. But if we add those all up, we get 6 over 6, which is 1. Same thing for flipping a coin, a little bit more manageable, right? We've got 0.5 and 0.5, next one. So if you ever add up your sample space and find that the probability is not 1, you're missing an outcome somewhere. Any questions about that? So, just some terminology. So 2 outcomes are disjoint, right? Or we could say mutually exclusive, whichever you'd like. And you've probably heard the terms mutually exclusive, right? Or I think when we're talking, we would say mutually exclusive, but disjoint means the same thing. And it just means that 2 things, so these 2 things can never happen at the same time. Right? So for example, you flip a coin, right? Heads and tails, they're disjoint. Because if you flip a coin once, you can only get 1 of those outcomes. Same thing with rolling a die, right? You can only get 1 of those outcomes. And so here, if you flip a coin once, you can only get heads or tails, just using H or T, but not both. Pardon? Then you wait. I think, didn't they do a study, and I think that happens like some very, very, very tiny proportion of times, but I wish I could remember how many times, but it's very rare. You should probably take a picture and then wait. So they are disjoint. Just some more terminology. We'll talk about events, right? So we're not just interested in rolling just a 1, a 2, or 3, or 4, or 5, or 6, right? Sometimes we might want to know, okay, what's the probability of rolling a 4 or a 6, right? So I've put money on both of those. What's the probability of either of those happening? Again, they can't happen at the same time, right? But I might be interested in more than one outcome, right? And so then I'm interested in an event. Okay. So events, I have there's sets of outcomes or collection of outcomes. So if I am interested in more than one outcome, I'm interested in an event. So let's just say, right, I'm interested in, okay, well, what's the probability of rolling a 4 or a 6? We can just say, okay, well, I'm going to denote that by B, just picking a letter, it doesn't matter. And if we wanted to, we could use set notation like I have here. It's not something that I expect you to know, right? But here we're just denoting a set of outcomes. Right? So B is a set of 4 or 6. But what we're more interested in, right, if I asked you to find this, so what's the probability of rolling a 4 or a 6? You would probably say, well, the probability of rolling 4 is 1 in 6, and the probability of rolling a 6 is 1 in 6. So I can just add those together, right, because I've expanded the outcomes that I'm interested in. And so the probability of 4 or 6 is 2 over 6. What we'll see, just in about 2 minutes, is that we can only do this if we have disjoint outcomes, right? So we can only add up these probabilities individually, right, if the events are disjoint, okay? So we can only do this if the outcomes are disjoint. See how this deck of cards printed. Well, you can't see the color, but pretty good. Okay. So what happens if things aren't disjoint? Right? What's that gonna look like? And so I'll just make a note here so you'll see it on here, but these are red and these top 2 rows are black. So we've got a standard deck of cards. There's 52 cards, and we can talk about, well, there's 4 suits, or we can talk about face cards. Again, we can talk about the colors. So there's lots of things that we can talk about just using a deck of cards. But what if we want to know, okay, so I'm drawing a face card, so I want to know what's the probability of drawing a face card, but I also want to know what's the probability of drawing a diamond. So here we've got all these diamonds, and here we've got all these face cards. Because there's this overlap here, we've got overlap, meaning face cards and diamonds can happen at the same time, right? So F and D, right? Just referring to I said if we let F be drawing a face card and D be drawing a diamond. So F and D are not disjoint. So this is going to behave a little bit differently than what we've seen so far. We can still figure out the probability of just a face card, right? The probability of a face card, we can add up how many face cards there are. There's 12 out of 52. So we can just say the probability of a face card is 12 over 52. And the probability of a diamond, there's 13 diamonds out of the 52. So the probability of drawing a diamond is 13 over 52. And those are here. So individually, we can figure out what those probabilities are. And that's still true, even if they're not disjoint. Okay. So here, if we're thinking about in terms of F and D, right, the overlap is where we have a face card and a diamond. Right? And so here, we've got F and D. And I'll put quotes around it because that's going to be a concept. Right, where face cards happen at the same time as the diamonds. We can find the probability of that. There's 3, right, that are in the F and D category. And so the probability of F and D is 3/52. So if I want to know what's the probability of F or D, and I just had to count them, then I would go, okay, well, there's 13 here. So that's all the diamonds, or the rest of the face cards, right? 13, 14, 15, 17, 18, 19, 20, 21, 22. Right? And so you could just look at it and say, well, the probability of a face card or a diamond is 22/52. Right? And so that's the note I have here. By simply counting, we would find 22/52. Whereas if we tried to just add this up, 12 plus 13, we wouldn't get 22 out of 52. Right? But that's because we have to subtract the overlap. Right? And so we only counted this section once. So how I like to imagine it is you've got, you've counted it once, and then you've counted it again, and so we subtract the overlap. Okay. And so here, that's what we're doing down here. We have to subtract the overlap. Because it's overlap, it's essentially there twice, right? So you're just removing one layer of it to make it smooth, or at least in my mind, make it smooth. And that's how you would get to the 22/52. So in terms of formulas on your formula sheet, we'll come back to the others up top, but you've got the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. And then we've got the special property that if A and B, so now we're talking in general, right? Any events or outcomes A and B, if A and B are disjoint, then the probability of them happening together must be 0. Which I think if you're given the definition of disjoint, right, they can never happen together, you would probably arrive at that probability being 0 anyways. Right? So that's just something to keep in mind. Right? And that's why earlier when we were able to just add up the probabilities, that's the reason, right? Because the probability of a 4 and a 6 happening at the same time is 0. So it was 1. So in terms of what we have to do for answering questions with this stuff, right? I'll give you 3 of these 4 pieces, right, in a question, right, in a blurb. So the probability of this is this, the probability of this is this, and then the probability of this is this, and then you'll have to solve for the 4th one. And it can be any one of these 4 values. So just going back to the top of the formula sheet here, if you go to, I forgot to mention it, I think. I have it on here, but right? So the fact that a probability has to be between 0 and 1, that's on your formula sheet as the probability of A, so that's any A, has to be between 0 and 1. Inclusive. And that's the first thing on your formula sheet. So it's just math notation for saying a probability has to be between 0 and 1. Yeah. Oh yeah, these are yours. Yeah. Do whatever you want with them. No. Maybe at the end of the term, I don't know. But yeah, these are yours. And like I said, I might be adding stuff to it, so if we get a new formula sheet, I'll just give you a fresh copy. But same information, just potentially more. We also said that the total, the sum of the probabilities, the probabilities of the whole sample space S has to be 1. So if we add up all these probabilities, the total has to be 1. So those are the first two things on your formula sheet, and those are just the probability facts. So let's just talk about probability distributions. So a probability distribution is just a table like this, where you have all the possible outcomes up top and their probabilities down below. So in this example, we're talking about the sum. So you've rolled 2 dice, and now we're adding up the sum. Right, so we're adding those up, and the lowest possible total that you could have is 2. And the highest possible total that you could have is 12, right? 6 and a 6. So a 2 can only happen one way, right? 1 in 36. So there's 36 different outcomes that you could have, right? You could roll a 1 and a 1. There's only one way of doing that, a 1 and a 1. Here, for rolling a total of 3, there's 2 different outcomes, right? Because we could roll a 1 and a 2, or a 2 and a 1, right? Making 2 separate outcomes. The total's the same, 3, right? But that's why this probability is higher. And so you'll see that as we keep going, 7 has the highest probability of happening. Right? So definitely if you're betting, then betting on a 7, I don't know, you would likely win, right? But also that's often compensated by, well, if you do something like a 12, notice that a 12 has the same probability as a 2, right? So a 12 or a 2 or something kind of out in the flanks here, that's going to have a bigger payout than something in the middle that can happen in more ways. So that's kind of as far into card counting as we'll get. Those aren't even cards. I know. It's okay. So here we've got this probability distribution, right? So it just lets us look at the distribution of the probabilities. Right? So we've got each outcome and their probabilities below. The rules for probabilities apply as well as another thing. So for a probability distribution to be valid, each of the outcomes listed has to be disjoint. So you can't have any overlap in these outcomes. Each probability has to be between 0 and 1. Again, that's on your formula sheet. And the sum of the probabilities has to be 1. So those are all familiar. So here's kind of a common thing. I'll get you to do it on test 1. is just, I'll give you a probability distribution or 3 proposed probability distributions, and you have to pick which one is the valid probability distribution. And so first thing we have to check, right, is all these outcomes have to be disjoint, right? So there can be no overlap. So here we've got the income between 0 and 24,000 in thousands, 24,000, 25,000. And then 25 to 49, 50 to 99, and then 100 plus. So those are all disjoint, right? There's no overlap in there. And then, so that's step 1 satisfied, right? Next thing we have to check, any of these options that have a probability that's not between 0 and 1 is out. So it can't be this one. It can't be B. Because we can't have a negative probability. But if we check all these other ones, then those all look okay. They're all between 0 and 1. And so then we can move on to the next step and figure out what the totals are for A and C. And if they each have a total of 1, then they're both valid probability distributions. They won't, but I think we can just do it quickly. So 0.18 plus 0.39 plus 0.33 plus 0.16 is a total equals 1.06. So it can't be a probability distribution. So we'll check the last one just to make sure. 0.28 plus 0.27 plus 0.29 plus 0.16. Phew. The total is 1. And I've just gone through those points below. So C is the valid probability distribution. Any questions about that? Let's talk about the complement of an event. Complement of an event. Hard to say. So the complement of an event is essentially the opposite of the event. Right? So if I say, for example, if B is the event of rolling a 4 or a 6, then the complement of B is everything where I roll anything but a 4 and a 6. Right? So the complement, which we denote by a superscript C, or I've made a note here, sometimes I'll get lazy and I'll just do a B prime, right? So a little apostrophe. I'll try to stick with the C's because that's what's on your formula sheet, but if you want to do primes, you're allowed to. Sometimes it's easier to write B prime. But they mean the same thing. So the complement of B is just the set of events or the set of outcomes that are not B. So how I'm going to read it, right, is just not B. The complement of B, I'll just read it. Not B is 1, 2, 3, 5. And so we have this property on your formula sheet where if we know the probability of A, the probability of not A is 1 minus the probability of A. And we saw that just earlier, right, when I said, well, if I tell you that the probability of picking a male is 0.7, then you know the probability of picking a female is 0.3. Right? And so that's the complement of picking a male. And so that's the complement of an event. So we've made a good dent on your formula sheet, and we'll pick up with the rest. Yeah, we'll call it here. Don't want to start a new section. Make sure you do your assignment if you don't have a copy, or if you didn't get the front page last day, come grab it. I'll see you on Wednesday. Nice. Awesome. Thanks. Monday. Today. Oh, okay. I have a lab at 4 on Wednesday. Did you go to? No. Or I'll step this, and then